Welcome to Study Time, a televised home learning program produced by Rwanda Education Board.
Welcome back to this TV learning series program. My name is Teacher Patrick, and this time around I'll be taking you through Senior 6 Chemistry. And we'll be looking at together, because I'm sure that you could have even covered this when you are still at school. We would be revising together Unit 4. I don't know whether you still remember what Unit 4 is all about. Good. So Unit 4 is talking about benzene and its derivatives. So let's come back to the benzene and its structure and its derivatives. Basically, we'll talk about the structure of benzene. I hope you still remember the structure of the benzene, but if you have forgotten, I just want to remind you about the structure of the benzene. But before we go to the structure of the benzene, I want us to look at I just want to give you the historical background of the benzene structure. If you remember very well, in 1825, Mike Faraday was very well known for the conduction of electricity in solutions, what we call electrolysis. So he carried out a lot of experiments in electrolysis. And he's also well known for discovering the structure. He was the first person to discover the structure of the benzene, to discover the existence of benzene. In London, this was Mike Faraday. In London, from eliminating gas that was this is primarily the mixture of methane and hydrogen gas. So by that time, the structure of the benzene remained mysterious. Again, in 1834, this was a German physicist and chemist. He has very difficult name to pronounce. So he determined the molecular mass of this benzene and was found to be 78 grams per mole. So after determining the molecular mass of the benzene, then its structure was known to be, the molecular structure was known to be C6H6. When you look at this structure, if you remember the alkanes, if you remember the hydrocarbons, I hope you still remember the hydrocarbons, because those hydrocarbons were talked about in Senior 5. The compound of carbon with 6 carbon atoms, if it is an alkane, how many hydrogen atoms is it supposed to have? I hope you still remember. If it is an alkane, then it should have 14 hydrogen carbons. If it is an alkene, then it is supposed to have the 12 hydrogen carbons. So after discovering this structure, the molecular formula of the benzene, you look at it as the compound with high degree of uncirculation. High degree of uncirculation. So the number of hydrogen carbon atoms in relation to the relation to the carbon is few. And then unsaturation means that this compound should be having at least some multiple bonds. And basically, we are talking about the double bonds. I hope you still remember with their alkenes. So looking at this structure, even from when the molecular formula was known, the structure remained mysterious, not until 1865. In 1865, that is when August Kekule, this was a German physicist, was able to identify, that was the first chemist to propose the structure of the benzene. And can you imagine, can you believe this? This came into his dream, that the structure of this benzene, which was not known almost very many years, from 1834 to 1865, those are very many years. So he thought that the structure of this benzene should be similar to, if you consider a snake chasing its tail. When the snake is chasing its tail, then it is moving around in circular form. So that is how, in his dream, it came into his dream. I thought you would be even dreaming chemistry maybe tonight. That would be my wish. So in his dream, he thought about that, a snake chasing its tail. And he came up with the structure which is similar to this. So this is what he came up with, that the carbon atom, the 6 carbon atoms, were arranged in a hexagon with hydrogen on each carbon atom. There was a hydrogen atom attached on it, and with alternating double and single bonds. So if we say alternating, then it means that if the double bond is here, this is the double bond, which is alternating with the single bond. A double bond, a single bond. A double bond, a single bond. So this can also be represented in this form. Remember, on each carbon atom, there must be a hydrogen atom attached on it. And that is on the corner of the hexagon. So that one is alternating. These carbon and single bonds are alternating with one another. This can also be simply represented in this skeletal form. You say this is a skeletal form. It means we are not showing the number of carbon atoms or the hydrogen atoms, but we can still show the alternating and single bonds. So that is the structure. This is the structure that Kekure came up with. At that time, that was a very important achievement because it has sense with the modern structure of the that we are using now. However, some of the chemists never agreed with him for some reason. So they disagreed with him for some reasons. And these are some of the reasons that even Kekure's structure was not the perfect structure of benzene. And this is what we are just going to look at, why even the structure that Kekure brought up is not actually the perfect structure of the benzene. If you remember, the reactions of alkenes. Do you still remember the reactions of alkenes? Very good. So I think you've said it, right? Electrophilic addition reactions. Electrophilic addition reactions, whereby the electrophile adds to an alkene. When the electrophile is added to an alkene, so in the experiments that were carried out at that time, it was found that this benzene does not undergo electrophilic addition reactions. If probably I can still remind you of some of the electrophilic addition reactions. For example, if you have an alkene, alkenes have double bond. And if you add an electrophile, this electrophile is supposed to add to the carbon-to-carbon double bond, and the electrophile will be added there. The electrophile will also be added on, and the double bond breaks. So that is how it was found that benzene doesn't undergo similar reactions like the alkenes. And even some of the experiments that were carried out, you know, when alkenes react with bromine, reaction with bromine, when you react it with the alkenes, do you remember what happens? Perfect. The bromine color disappears. It was decolorized. Even when we use the cycloalkene, this is an alkene that is also cyclic. It has some similarity with the benzene because the carbon atoms are within the ring. Even when you react it with bromine, the bromine is decolorized. The bromine is decolorized. But for the benzene, if the reaction takes place with the benzene under room temperature, this benzene, when it reacts with bromine, at room temperature, no observable change. No observable change. And what does that mean? It means that probably there is a problem with these double bonds that we have. It means that these double bonds are not the same. Even when the alkenes are subjected to the strong oxidizing agents. Do you remember some of these oxidizing agents, students? Very good. Some of those ones, we have potassium permanganate. We have the potassium dichromate. So when they are subjected to these compounds, an alkene is passed through this. This is purple. So the purple color fades and then it turns into the colorless. Do you remember what happens with potassium dichromate? Very good. So the potassium dichromate is orange, yellow. So when the alkene is passed through this potassium dichromate, then it turns into green. When even these were subjected to benzene or with benzene, no decolorization took place. Why? That was a problem with Kekure's structure. Because if this Kekure's structure, if they are alternating double and single bonds, then we would expect this compound to behave like the alkenes behave, because they have the same double bonds. Another problem with the Kekure's structure was on the shape of the molecule of the benzene. If you look at the shape, normally, according to the X-ray diffraction analysis, the carbon-to-carbon single bond, that is the length, this length is equal to approximately 1.54 nanometers. You remember 1 nanometer is equal to 10 to power negative 9 of a meter. That is a very small distance. The double bond is supposed to be approximately 0.34 nanometers. And according to the X-ray diffraction analysis, it was found that the bonds in the benzene, or these bonds that we talked about in the benzene structure, all these bonds were equal. This bond was equal to this. This single bond and the double bond had the same length. So the carbon-to-carbon double bond, or the carbon-to-carbon single bond in benzene, was found to be around 0.39 nanometers. This is somehow between this one and this one. So it was not the single bond. We have the single bond right away. Look at the structure of the benzene. If the Kekure structure was correct, then that means that this benzene would be an irregular. It wouldn't be a hexagon. When we talk about the hexagon, you remember this is primary. From your primary, you know the hexagon is supposed to have equal size, the equal sides. So, according to the Kekure, this structure should be irregular because the double bond and the single bond do not have the same distances, do not have the same length. So the length in here was found to be 0.39. That is the length is in between. And therefore, that throws even a lot of doubt on the Kekure's structure. We'll talk about the chemical stability of the benzene. And I just want you to look at this. Maybe this data is indicating the energy. This is the enthalpy of hydrogenation per 1 mole of carbon-to-carbon double bond. That means that for one double bond to be broken, in this compound, but2-in, this is the amount of energy. And because we have only one double bond, that's why we have the same figures. Negative 119. This is cyclohexene, which is similar to slightly similar to benzene, has some similarity with the benzene, then we would expect this is negative 118. This is negative 118. So because we have only one double bond, so to break that double bond, this is the amount of energy. When you look at this but 1,3-diene, to break one double bond, we need negative 118. This is twice this one. Can you look at that one properly? This figure here, 236, this one is twice this. What does that indicate? It means two double bonds are broken. Therefore, the figure, the enthalpy of hydrogenation for this compound, but 1,3-diene, is twice this one because of the two double bonds. Just take a look at this one, cyclohexadiene. That one has two double bonds. We have a double bond here and another double bond here. So one double bond, to break one double bond in that compound, we need negative 116. So if there are two, then this is negative 232. That makes sense because this figure is twice this one. I hope you can, this is just arithmetic, just multiplication. Multiply this one by 2, so you'll get this. This is the enthalpy of hydrogenation. When it comes to this compound, which was proposed by the Kekure, remember, which he thought is the benzene, to break one bond in this compound, this is the assumed value, negative 118. Then, if we break 3 bonds, we are supposed to get 354. This is the assumed. Look at this structure again. Can you just come at this chemical interpretation of this benzene? Compare this one, this structure, cyclohexatriene, because it is triene because it has 3 double bonds. That is what Kekure proposed. And then let's come to this. When we come to this one, this is the values are coming from the other one. Let's first take a look and just very keen look at this compound. This is the structure we are talking about for this is the proposed structure for the Kekure. When the 3 double bonds are broken, we are expecting the amount of energy that is released is supposed to be 352. But it was found that benzene, the actual benzene, when the 3 bonds are broken, the amount of energy that is released is negative 205. That is slightly lower than the expected. And why is that one? So that even throws even a doubt on the Kekure's structure, because it is supposed to be the same. So that means that in this compound, the number of bonds which are here are not exactly, these bonds are not double bonds. So we call this difference the stabilization energy, or we call it delocalization energy, or the resonance energy, meaning that benzene is more stable than expected from the structure of the Kekure. The lower, maybe I can just mention this, the lower the energy, the more stable the compound it is. When you look at this one, this is lower than this, so that means this compound is more stable than this, and that was benzene. So those are some of the reasons why benzene is more stable than the expected Kekure's structure, and that one of the reasons why benzene, the structure of the benzene remained a mystery for even some time. So I'll just look at the modern structure of the benzene. If we take an example of this is the hexagon. On each corner we said, you remember we said there is a carbon atom. So on each carbon atom, when you look at this carbon atom, there is a hydrogen. So there are 3 carbon uses. Look at this structure here. This is a bond. This is another one. This is another one. So the carbon is sp2 hybridized. That's a trigonal prana, if you remember. sp2 hybridized. So the 3 electrons out of the 4 are used. So where is another electron? It is in the p orbital. This is the p orbital that contains the extra electron. So when you look at these orbitals are laterally placed. They are parallel to each other. So this orbital, because when you look at this one, we just try to magnify it, but the distance here is very small. So we'll see that this orbital here overlaps with this orbital. And you see this one also will also overlap with this. This one is also lateral to this, so they will also overlap. So this one overlaps with this one as well, and then it overlaps with that and this one. When you look at that one, you will see that it forms some of a circular form on the upper part of the carbon plane. And then you have this one overlapping. So when we have this one overlaps with this, it overlaps with that, and then overlaps with that, and then overlaps with that. So there are 2 robes that will be formed on the lower part and on the upper part. So this forms what we call the pi system. The pi system, or what we call delocalized electrons. Delocalized electrons that make the pi system. So this was the modern, and this delocalized system, the delocalized system of the electrons, is the one that brings about the stability that we talked about, and this is the modern structure of the benzene. This was proposed by a very strong female chemist called Catherine Linsdale. This was just recent, 1928. So as we probably coming to the end of our lesson, which was about the structure of the benzene, and basically about the Kekure's model structure, we are going to look at some of the homework that I've left. Part A is talking about benzene has the molecular formula C6H6. Draw the Kekure structure for this, showing all the atoms. B, now draw the skeletal structure showing the way the Kekure structure is normally drawn. If you look at number 2, ethene and benzene react with bromine in quite different ways. With ethene, bromine reacts with addition reaction. That is the reaction with bromine. And with benzene, you get substitution reaction in which one of the hydrogen atoms is replaced by bromine. Explain this. Explain this, why this throws doubt on the occurrence of the Kekure structure. So we've come to the end of our lesson today. I thank you so much for listening and watching. I hope we'll meet again in another episode. Thank you so much.